uh, back to filling up the details in this picture, basically. That's what we'll do over next half an hour or so, and then maybe play around a little bit with the algorithms that I have put up, Kalman filter and ensemble Kalman filter. Though that's order. This was just the good old Kalman filter, and this is the Monte Carlo version of it, which is the ensemble Kalman filter. So those are the two things I will basically focus on. I will not talk about particle filter. I don't think I have time to discuss it in any great detail. Okay, so the picture. How do we fill up the picture? The idea is basically a recursive algorithm or to construct a recursive algorithm such that suppose you have a distribution at some time, and that distribution can be used to make a forecast using the Markov model. That will be these green distributions. Right now it looked like bimodal, I don't know why. And using the observation at that time, you make an update which is using Bayes theorem and keep the process going as a recursive process. So that's what we will fill up as details. What to do, right? Okay, so just some notation. The A, superscript A, indicates analysis, sometimes called update, and so on. Essentially, it's a distribution, it's a filter. It's a distribution of the variable at time t, the state variable at time t. Oh, t minus 1. It's a variable xt minus 1 conditioned on the observations up to time t minus 1. So it's xt given y up to time t minus 1. That's what is called analysis or update. Using that update, we want to go forward in time as a forecast. So that's why PF, the F is for forecast in the middle distribution. So that's the distribution of the state at time t given observations up to time t minus 1. So y1 is to t minus 1 is basically observations up to time t minus 1. And using now the forecast and the observation, so I didn't put an arrow coming in from the observation. So there is observation being incorporated at that time, which is yt. Using the observation, again, we generate analysis at time t, and then the process repeats, and this will be the sequence. Right, the first part, straightforward. Basically, it's a Markov transition kernel. Or Markov, in this case, I'm writing everything in terms of densities. So it's just the Markov model applied to the distribution PA. So the distribution PA times the Markov transition density integrated over t minus 1 is the forecast. And practically, what this will really mean is essentially what is called integrating the model forward in time. That integration dxt minus 1 is basically the model integration, solution of the ordinary differential equation, solution of the partial differential equation, or solution of the stochastic differential equation, whatever it is that you have. Right? So that integral is the dynamical model part of it. And the update simply uses Bayes theorem. So the forecast is the Bayes theorem in the following form. The density of, how should I write it? A random variable A given, so A given B is proportional to the B given A times. Let me change the order. I changed the order for following reason. Essentially, A is now, so if you want to do a pattern matching, A is xt given y1 through t minus 1. And B is just yt. And then put that in, and that's what you get. Yeah? So the forecast, so this will be the forecast, PF, and this will be the observation and likelihood. So if you do this translation correctly, then that's what will turn out to be. So this will be the forecast is the prior, is what is called prior in Bayesian method terminology. And this will be the analysis. I use an, yeah. Or the posterior. Again, in the Bayesian terminology. So this is just the use of the Bayes theorem. Yeah? Question, please. Yeah, so what is, yeah, okay. So why does it look like this? Why does it look like y given xt? Yt given xt? So I said A is xt given all of these things. But now it will be B given xt only because of the assumption about the Markovian. So I guess I did not specifically give the assumption. Okay, so I guess in my mathematical framework, I did not specify the assumptions needed to get this formulae. What is needed is to say that the eta t variable, so the model was written like this. Yt is h of xt plus eta t. The assumptions needed are that eta t goes from say 1 to t, and not, okay, in terms of random variables, I need to write it slightly differently, but slight misuse of notation. I'm going to now write down here probability densities. Sorry about that, because I didn't introduce the notation in terms of random variables for the Markov chain, but up to a slight misuse of notation, so the Markov transition, the Markov chain for the x variables and the observational noise are independent. So that's the assumption that's needed to reduce this term from get rid of these terms and just have yt given xt. So there's 1 or 2 lines of calculation missing to get this, but and the assumption that goes into that 1 or 2 lines of calculation is basically just this, that the observational noise is independent of the Markov chain we are trying to observe. And since I didn't write down this in terms using random variables, that's why the mixture notation appears here. Sorry. Okay. So the outcome of all this effectively is as follows, or basically the mathematical statement turns out to be P of yt given xt, comma, anything else. So let me just write anything, A being whatever other random variable that you wish, it's simply equal to P of yt given xt. And this is all we need to get that. Okay, so actually, basically a similar assumption is needed in the first step as well, because we have it's xt given xt minus 1, and that follows also from the Markov property of the x process. So that a few lines of calculation missing to get these. This is a result that follows after not very difficult, but just a quick calculation. Okay, so but it's a natural. I mean, it's something that's kind of obvious to explain, or it's very intuitive result. And that basically is what gives the recurrence relation, which is if I have the posterior or the analysis at time t minus 1, okay, I should do this with mouse. So if I have the analysis at time t minus 1, then integrate the model forward in time, that's the first part, and then multiply by the likelihood, P eta is called likelihood, multiply by the likelihood of the observational noise, and that gives the posterior or analysis at time t. It's a very, intuitively simple process to think about. Yeah. This is just a picture for a recursive. Actually, sorry, I thought I had another picture. I have a whole variety of different types of pictures available, but anyway. So, what's Kalman filter? The Kalman filter is the case when everything is linear and Gaussian. The one-line summary of that. So, if the Markov model is Gaussian, the observation operator is linear, the initial distributions are Gaussian, and the observation noise is also Gaussian, then if you are starting with the initial Gaussian distribution, at every step, the forecast and analysis, then the forecast and analysis, they remain Gaussian. A fairly straightforward fact to prove, if you happen to know the fact that Gaussian distributions form this family of closed distributions under the Bayes rule, and also under products. So product of Gaussian densities is Gaussian, and integrals, marginals of Gaussians is Gaussian, and so on and so forth. So a few, 3 or 4 fairly common properties of Gaussian distributions gives this result that if the initial distribution is Gaussian, then under a Markov transition kernel, which is Gaussian, everything remains Gaussian. Okay, so all we need to deal with for a Gaussian distribution are the means and the covariances. So this is where the covariance will make its appearance for now. So we represent everything in terms of the mean and the covariance. So for PA, there will be mean and covariance, which will get a superscript A. For the forecast, there will be a superscript forecast for the mean and covariance. And that's the standard notation that will be used in the rest of the slide, right? So the analysis mean and covariance has a superscript A for analysis, the forecast for F, the superscript F is for forecast, and the subscript is for time. Plethora of superscript and subscripts, but unavoidable. And then a few lines of Gaussian calculations, basically completing the squares. That's all that you need to do. Once you know how to complete the squares and then integrate, these formulae follow pretty straightforwardly. That the analysis mean is a linear combination of the observations and the forecast mean. And the analysis covariance is the forecast covariance minus a positive definite part. So in fact, the analysis covariance is less than the forecast covariance. I haven't proved it, I'm just stating it. So KHCF, even though it doesn't look like it doesn't even look like symmetric matrix for now. It is a symmetric positive definite matrix, a positive semi-definite matrix actually. So CA is less equal CF, that follows from this formula. The factor K, which is called Kalman gain, is written over here. I'm not going to go through these calculations right now. One of the things that is needed is what is called a Sherman-Morrison-Woodbury formula, which I didn't write down. And so I'm not going to derive this. There is another way to derive this, which is let me write it down at least so that I can make a connection to the variational methods. The same formula, so this follows from, what does it follow from? We know, so if the analysis mean and covariance is written like this and the forecast one is written like that, basically it follows from this formula. So the forecast has XTF and CTF as the mean and the covariance. This is a Gaussian distribution which has the mean, which is YT. So the mean of this Gaussian distribution is YT, and a analysis covariance, which I didn't introduce the notation, sorry. Maybe I did it, unfortunately. Wrong. No, I did not introduce that notation. Sorry, I forgot to introduce this. R in the matrix K is the covariance of the observation. So this is Gaussian with mean Y and YT and covariance R. And then just product of two Gaussians, complete the squares, and that comes out. The other way to think about it is as follows. We have, if you write a cost function, so I want to try to figure out how close I can get to observations while still being close to the forecast. So I want to find the sweet spot between the observations and the forecast. I don't want to go too far from the observations or too far from the forecast. How do I find the weightage factors for each of these? Those are given by the respective covariances. So essentially, it will look something like this: x minus x forecast time t, and then the weight factor for the forecast, C F T inverse x minus x t f. This will measure basically a distance of a state from the forecast. And I want to do the same thing for the observation. Sorry, yt hx. And again, weighted by the covariance of it. And half, why not? And write this as a function of x. The minimum of this object is exactly the formula written over there. So, firstly, this is a Gaussian, so it can be written in terms of, this is a quadratic form, and the quadratic form will have exactly the mean, which is XA, and Hessian, which will be CA. So, the minimum is, say, T, and the Hessian, it's a quadratic form, so its Hessian is independent of X, and that is, so that's another 2 lines of calculation. Well, maybe not 2, whatever number of lines. So both those calculations are essentially similar looking, but 2 different ways. So that is, if you actually do this in practice, that is, you write down this as a cost function and try to minimize it using some appropriate numerical method, that would be what is called a variation method, clearly. A variation method, because you are going to use the optimization algorithm to minimize that cost function. If instead of doing this at a fixed time, you do this over a whole range of time, so your observations over a time period, T1, T2, T3, T4, then you need to know how the covariance, the CFT that I wrote down there, changes with respect to time. And that's where the 4D var versus 3D var, which I mentioned earlier, came in. So the variation methods are basically minimization of cost functions of that form with observations that depend on time. And Kalman filter-based methods are analytical formulae for the minima being used in terms of the actual forecast mean and covariance. So that's basically the difference. For Gaussian problems, they are identical, in theory, identical answers. In practice, there are difficulties in terms of, suppose you are not able to use the optimization sufficiently proper. You can't find a global optimum, for example, and so on and so forth. So there are approximations to be done there. Okay. So I think I will skip for now I'll skip the Jupyter notebook for Kalman filter. It's a fairly standard exercise in, I don't know which class, control theory? Somewhere. Sorry? Linear systems, yeah. So I'm not, yeah. I'm not taught this class as an engineering class, but so I'll skip this notebook, but let me just quickly mention what this contains, and I will not actually do it. It's basically essentially a solution to the exercise from that book, which I mentioned in the note in this. This book is available online, PDF, and this is the exercise from that book. And it's simply trying to implement Kalman filter for a specific linear model, which is given over here. So let me jump to writing. Okay. So here is the Markov model. So let me mention the observations first. Yt is hxt plus eta. That's this part of it. And h is just observing the first component. Then xt is a xt minus 1, the linear bit, plus some other random variable, I don't know, symbol, invent a symbol for that. But both are Gaussian, so it's a linear Gaussian model. and then just implement Kalman filter for this, and this is what this notebook contains. Yeah. Okay, I'll leave you to look at it later.
So I heard that this is the thing that was used for the rocket that went to the moon.
Yeah, that's true. Yeah,
So
it is. Yeah, and the models are not linear there. So what is the in many okay? So maybe I'll mention what happens when the model is not linear. So in practice, many times the observation operator being linear is not such a big assumption, because that typically you would have a big system, you will observe some parts of it. For example, for the moon rocket and part, the state vector is position momenta. What you will observe is just position, and based on position, you would want to control the rocket. So that part is not, but the model is typically non-linear. So what do you do for the going forward part of it? The main assumption there is that if you have sufficiently frequent observations, okay, so think of what does I did not write down the going forward part. So if we have this map from the analysis to the forecast, and this is the map going, this is basically the model integration. If this is Gaussian and you are going forward for a sufficiently small time by a nonlinear model, effectively linear approximation kicks in and this remains close enough to being a Gaussian, and then you can use this and everything remains close to being Gaussian and Kalman filter still works. And this is this in fact actually also is applicable when the observation operator is nonlinear. You can linearize if it's not sufficiently, if the observation is not too far from the state estimate, then you can do a linear approximation near the state estimate, and then you are still in the linear regime in some sense. Effectively, Taylor expansion works, and then that is what is called the extension of this for what I just said in how to implement this in practice is what is called extended Kalman filter, EKF, and that works reasonably well if you have frequent observation, because then you then this deviation from non-Gaussianity is not very severe and Kalman filter works well. Yeah. So that was used, well, it's, I mean, not just used then in the moon, it's used to control rockets even now. So that continues to be, this continues to be a workhorse for space science, and this is now a old, very old tool. It's as smooth and easy to use and so on as the umbrella or something. Right? People, you don't think about how to use it, you just use it and it works. It stops you from rain. And that's it. Okay. Yeah. So, where is what's the problem then? Why don't we use this for weather forecasting? Any guesses? We should just then, I mean, if it works so well for rockets, we should just use it for weather as well. Non-linearity is a problem, fine, but maybe suppose you do very frequent observations and something like that. But actually, frequent observation is one of the problems, but leaving aside that one, there is another really difficult problem. Sorry, I can't hear. Okay, so Gaussian. Suppose by some chance, maybe you are, let's say you are dealing with Gaussian. Even if everything were Gaussian, this is still a problem. Why? No, the weather models are actually Markovian. They are PD, Newton's laws, and so on and so forth. So that's not a problem. Something else is a problem, which is this. What's the size of this matrix? It's the state space cross state space. If D were 10 million or 100 million, you want to do this for a 100 million cross 100 million matrix. Okay, even if things were slightly sparse and so on, okay, it's of course positive definite, only store half of it or something, but still, this is simply not possible to do effectively. And on top of it, getting good estimates of covariance is not easy for a 100 million cross 100 million dimensional problem. So covariance estimates and actually storing and dealing with covariances is a huge problem. In addition to being everything else that you had, that some of you mentioned, Gaussianity, That's not obvious. Non-linearity is an issue, and so on. Right? Sorry? Oh, why is it? So think of how do you solve a partial differential equation? So as I said, the models are something like, say, Navier-Stokes equations, partial differential equations for temperature, velocity, and so on and so forth. So now you want to solve the partial differential equation on the surface of the Earth. So let's say you make a grid, and the grid resolution is 100 kilometers by 100 kilometers. That gives you something like about a million of 10 million grid points. I forget how many, but of that order. Does that answer your question? So it's a partial, we are dealing with a system which is essentially a partial differential equation. And that's of the size of what's the radius of the Earth? 36,000 kilometers, something like that. Sorry, that's the circumference. Yeah. So then this is where the ensemble Kalman filter comes in. If this sounded like a bad idea, just 1 second. If this sounded like a bad idea, this should sound like an absolutely terrible idea. But anyway, yeah, question. We would want to localize. And that is implemented in practice. So actually, the notebook that I'm going to talk about will include localization as one of the features. I'll also mention the difficulties with localization. But yes, so the weather is local, and that somehow needs to be used in practice. How to use it in a mathematically sound way is an open problem. There simply is no theoretical understanding of how to localize. Right now, it's very ad hoc. We would want to make it local, and hence let's make it local, and that's about it. Okay, so I'll mention how to implement localization. So what's a Monte Carlo approximation? A Monte Carlo approximation will basically represent the distribution in terms of sample points. The sample will be, in general, weighted. So these will be important samples. I did not have time, I don't think I have time to talk about important sampling in any great detail, but effectively think of this as each sample has a weight proportional to how important it is with respect to the density that you want to actually sample. So each of these distributions will be represented by a weighted sample or an importance sample. And with respect to some appropriate importance sampling density that I'm not mentioned here, but so the sample will be X, and now just way too many superscripts and subscripts, because now you need to add an index for the sample point. I goes from 1 to n. N is the sample size. Okay, so and the representation is that we would want this sample to approximate the actual distribution in an appropriate sense, in some metric that you would choose, and so on and so forth. So, so two important classes of methods are, one is the ensemble Kalman filter, and this is as simple as you can think about, which is that for every sample point given over here, attach a weight which is just 1 over n, so or basically not an important sample, but just a regular sample out of the density, and apply Kalman filter formula to each of the sample points. That's it. There are tricks to how do you compute k without computing the covariance. And that's a fairly straightforward calculation. It's not very difficult at all. It's in terms of the square roots of the matrices, and square roots can be easily computed from sample points. And so if you know a little bit about how to compute square roots of covariance matrices using samples, then that's basically what goes into this, but fairly straightforward computation. So the main point is that to compute the Kalman gain, K, you do not need to compute the covariance matrix, which is what I said is humongous. It's too large to even do anything with. So, okay. So that's one thing. And why does it work? I have no idea. And the I is actually slightly larger. That is, in fact, it's really not well understood why Kalman filter works well. Sorry, ensemble Kalman filter works well. Okay, and the other idea would be particle filter. So what happens in the Kalman filter? Essentially what happens is the weights always just continue to remain 1 over n. So it's not an important sample. And the sample points move around. So a picture would be something like this, that you have these sample points at time t. When you do the update, the actual position of the sample points will change. That's the xa. And then they will go forward in time. And then again, at the next observation time, the sample points, you change the actual sample. And you keep doing this in time. So the sample points, essentially what you get are discontinuous trajectories of the system, right? Because there are discontinuities going from xf to xa. And the discontinuity is proportional to the distance from the observation. But it's a linear combination. So that's the property of ensemble Kalman filter. The particle filter is simply that you change the weights. So it is effectively changing the importance sampling density that you sample with respect to, but keep the sample points the same. So these give you continuous trajectories, only the weights keep changing. I'm lying partly in the sense that there is something called resampling that needs to be done. I'm not going to talk about resampling here. So, but, okay, so the main crux is that ensemble Kalman filter changes the sample points, particle filters change weights. And, okay, so here is the one slide summary of importance sampling and how it is used in particle filters. So if XF is the forecast is actually not a sample from the original density that you wanted to sample, but a sample from some other density, which here I'm calling importance sampling density, call it Q. Then in order to get an appropriate weightage, an appropriate sample out of the forecast and then eventually the analysis, you need to adjust for the fact that we have importance sampling density rather than the original sample. So the heuristic is fairly straightforward. So let me just write it here for now. What do we use sample as a sample for? Basically to compute integrals, right? Or compute expected values of the random variables. So if you want to compute the expected value of, let's say, f of x with respect to a density, which is say pf of x, I'm going to drop all the other conditional terms and so on. This is what we want to compute. Then it is also equal to with the appropriate conditions on absolute continuity and so on. This is just a simple algebraic manipulation. And now you think of a sample out of a density Q instead of the density that we actually wanted, which is PF, and attach, and this is the function that we want to integrate, and then attach a weight which is proportional to PF divided by Q to each of the sample points. And that's essentially what goes into getting this factor, the factor that lies over here, which is the 1 over Q comes from that factor, the 1 over Q in the integral over there. Right? So if you want to compute expected values, you can convert all of this now in terms of sums. Right? So the integrals will become a sum when you write in terms of these distributions, in terms of sample approximations, the sums of Dirac deltas that I wrote earlier. And then this formula follows in a straightforward way. So combine the base theorem with this formula, but in terms of sums, using delta distributions. If you would like, yeah, this is a slightly longer calculation than most of the one-line calculations I've been mentioning. So I have a mistake here, which is that this should have been, okay, actually not quite, yeah. So the analysis, the weights at time t minus 1 are related to the weights at time t by a factor which incorporates that you want to go forward in time. That's a Markov model. Multiply by the posterior at time t, which is incorporating Bayes' theorem, and the 1 over q in order to incorporate the fact that we have a sampling, important sampling density that we use to get the samples out of. Yeah? Okay. For now, forget the last line. Resample if necessary. I don't, you know, it will take a little bit more time to explain than I have right now. So let me skip that. And this is a different, sort of a completely different way of approaching the problem. The ensemble Kalman filter is a purely linear kind of argumentation. This is a much more probabilistic argument. So very different ways of thinking about the problem, but both of them give you a Monte Carlo approximation to the problem at hand. Okay. And in practice, in particular, the ensemble Kalman filters are, as I said, implemented using square root filters because you actually compute the square roots and not the actual covariance matrices with what will be called inflation and localization. So localization I will introduce. And for that, I will need to go to the Jupyter notebook. So let me do that now. Actually, before going to the, so let me just quickly mention some of the theoretical properties of these filters. The Kalman, the particle filters, of course, the sampling errors, 1 over square root of n cannot go away. So the errors in the filters will remain at the level 1 over square root of n. N is the sample size, that doesn't go away. But unfortunately, the constant c, the error that particle filter makes, grows exponentially in time. And sorry, so it grows exponentially with two things. It grows exponentially with time, but it also grows exponentially with respect to dimension. So is there any hope at all that we can use it for 10 million dimensions or something like that, right? So that's the open question. Designing good, so to say, good algorithms for high dimensional systems that use particle filter ideas. They are not exactly particle filters, but similar ideas like particle filters for high dimensional system is a essentially completely open problem as of now. One of the only answers that I know of where the exponential growth with respect to dimension can be avoided is this one single paper. As far as I know, that's just the only paper, literally the only paper, where there is at least some hope of trying to overcome these exponential errors with respect to dimensions. But this, the assumptions needed in order to get these results were sufficiently strong that they have not yet been usable in practice. So who knows? I don't know how, whether this can be done or not, and so on. Completely open problem, effectively. Okay, but then it doesn't need anything about linearity and so on. No assumption about linearity is needed. The ensemble Kalman filter is clearly motivated by Kalman filter. So it's in fact motivated by things sufficiently close to Gaussian, but for reasons which are again not understood at all, seems to work very well, so sufficiently well, even very high dimensional systems. So for example, with systems with something like this 10 million dimensions, a sample size of 100 is what is used in practice. Something that Sandeep was asking. So you choose an ensemble size of 100. Use it for a system of million dimensions. That's just laughably ridiculous, right? But they seem to give a reasonably good answer. And this is where all the details about what direction should you perturb in, and so on and so forth, go into details. And part of it is where do the instabilities lie? So the instabilities of the dynamical systems and the behavior of this ensemble Kalman filter is very intimately related. I do not have time to explain. But hand wavily is something like follows. If you have instability, the errors will grow in that direction. If you have stability, the errors will decrease in that direction. And if you can follow, if you can understand the behavior of instabilities, that helps you understand the behavior of uncertainties in these systems. That's just like a summary in the sentence, but there is essentially no mathematical theorem that says why they work well.
To understand your point, which you just said, so earlier in the previous class, you had said that unstable systems are easier than stable systems
To control.
To control.
Yes.
And I guess the reason you're saying is that if it's not stable, then a little bit of perturbation will give you information. Is that what you're saying?
A little bit of, yeah. So a little bit of perturbation will, and its dynamical evolution will give you information that you can then use. Right? And that is also partly what is used in control, that you know how to control it well at the unstable points, because you effectively know which directions you need to control, which are the unstable directions, and exactly how to control. Unstable control and estimation are essentially dual problems, right? So the reasons for why the role that instability plays in these estimation problems is not quite the same as what the role that it plays in control systems, where you actually want to. These are uncontrolled systems that you are trying to estimate, and that's quite different from the other situation, right? So I think, I don't know if I can draw a very nice parallel between the two as such,
but like, okay, maybe a different question. Is there like a theorem which you can, a paper which you can point us to where this is a thing?
So for the filtering problem, most of this is really not a theorem, but more of numerical observations. Yeah, so these are numerical experiments that you can perform and figure out what's happening and so on. There essentially is not really much of a theoretical justification for the nonlinear systems. For linear systems, I can point you to references where how it works out. Because for linear systems, because you can basically do most of the computations by hand, you can understand what the role of instabilities is. That I can point. I haven't put those here. Yeah. For nonlinear system, there is really no good theorem per se, numerical experiments.
And what about the control part?
Oh, the control part. I don't know the paper. I don't know where to look. I will have to. I'll have to think about it.
Sure.
Yeah, I will ask Borkar.
Yeah, sure.
So yeah. Okay, so should we go to in the last 10-15 minutes? Go to the and I'll show you what works and how it works in practice. It's okay. Where is it? The ensemble convention notebook. Okay, so this is what it contains. Let me explain this part a little bit, and then I will show actually. As I mentioned that these are what are called square root filters. So how does it work in practice? This is what is done. So you take xi. I will not read the f for the forecast all the time. I'll just read the ensemble indices. So xi is the ensemble at time t. And you compute the mean x bar. And am I already out of time? Oh, okay, so just check. And xi minus x bar are the deviations. So you make a matrix with columns, which are these deviations xi minus x bar. That's a n cross d matrix or d cross n, depending on which way you look at it, columns or columns. So it's d cross n matrix. And that turns out to be the square root of the covariance matrix, right? And that's straightforward to show. So Z times Z transpose is the covariance, is the sample covariance. And so, so this is basically the square root of the covariance matrix already. And this is what I mentioned here, right? So P hat is ZZF transpose, ZZ transpose. And the steps written here can be, this is some bit of algebra that I'm not going to go through, but just simply define V to be HZ, transpose, and then do eigenvalue decomposition of that matrix, which is low dimensional because V, so Z, let's say is 10 million dimensions, 10 million cross 100. H maps to the observation space. So if you have 10,000 observations, V will be a 10,000 cross 10 dimensional matrix. Right? Or the other way around, there is a transpose to it. And so the eigenvalue decomposition of that matrix is not so complicated. Actually, wait, did I make a mistake? No, that's right. Okay, so yeah, sorry. It's not an eigenvalue decomposition of V because I was thinking, wait, V is not even a square matrix. V is rectangular. It's eigenvalue decomposition of V R inverse V transpose, which in fact is a symmetric matrix. So you do eigenvalue of this symmetric matrix V R inverse V transpose, call that C gamma C transpose, and write X to be this combination. I'm not giving any motivation whatsoever. I'm just throwing algorithms at you, but whatever. And then obtain Z analysis as the original forecast deviations multiplied by X, as defined over here. It so turns out that after you do a bit of linear algebra, that after you do these steps, the ZA transpose is in fact equal to I minus KH P hat F. So it's a bit of calculation, but not really complicated. And that's basically what I meant by square roots, that you have the square root of the original forecast covariance, and you find an algorithm to compute the covariance of the square root of the analysis covariance. And then you just use that, and that's it. So and of course, once you have the perturbations, analysis perturbations, you need the analysis mean, which can be again computed using this formula, which is simpler to compute than the original formulation in terms of the covariances. So here there are no covariances here. It's just the square roots that appear in this matrix, in this formula. And this is what is used in practice quite commonly. And some variations of these, there are more slight differences. And now let me say a bit about what I mean by localization. So here is the picture for localization. So suppose the X is, for example, think of this as temperatures over the Earth surface. So there will be some temperature somewhere. There will be some temperature in Mumbai and some temperature in, say, New York. So I'll just write this as Mumbai and New York, and so on and so forth. You would imagine that the temperature in Mumbai and temperature in New York right now are not correlated. If you compute the ensemble covariance, the sample covariance, then in the covariance matrix, so there is this EF, there will be entry corresponding to TM, T in Y, and TM, T in Y. And so of course, the diagonal entries should be okay. We want them to be okay. We want the entries corresponding to the cross covariance between Mumbai and New York to be small or 0. So if the physical distance along the surface of the Earth is large, we want the correlations or the covariances between those variables to be small. That does not happen in practice because, well, we're using ensemble size of 100. It's of course going to give you terrible estimates of the covariances. And that's what happens in practice. These turn out to be not small, even if we want them to be small. And the thing to do is to declare them to be 0. So that's basically what is done in practice. Localization, somebody mentioned, you mentioned localization. So the way you use local, you say that, oh, my information should be local. What do you mean by information? In this case, correlations should be local. Correlation of a random variable at some point with something far away should be 0, and then you just set it to 0. Adds, so to say, dumb if you wish, or clever. I don't know. There's a fine line between dumbness and cleverness. Anyway, and that is what is called localization in the ensemble Kalman filter, or in general filtering problems. That the correlation that's come out, and these are called spurious correlations, the things that you want to be 0 but turn out to be non-zero, and then you make them 0. That's localization. Yeah. I said inflation earlier. I'll talk about inflation in just a minute. Okay, so all sorts of parameters that are required for the algorithm. So I simply don't have enough time to explain each and every of these parameters that go into this algorithm. Sorry about that. I have like, what, 15 minutes, but anyway. The part, the method is in some sense straightforward. I have a dynamical model. That's why all of this is needed. I'm now going to use a model which is slightly different. Sorry, very, very different. It's not slightly different. And the model is, do I have, oh, wait, I did not write down the equations. Sorry, I forgot to include the equations in this. This is called another model by Lawrence, the same Lawrence guy who did the 1963 paper. This is from 1996. And this has the form that looks like follows. I'll just write a schematic of this model, which is it has variables x1 through say xd, a d-dimensional model, and it looks like this: xi dt. This is equal to, it's a function of xi minus 1, xi minus 2, and I think xi plus 1 or something like that. I forget, but some local set of variables. It's only variables plus minus 1 or 2 that are included. And what do you do if I equal to d? Do a circular. So all of these are, so you take I mod d, essentially. So think of this as a variable, so x1, x2, x3, xd, and then this is just circular, right? The motivation is to think of these as variables on, let's say, a latitude circle, for example, or on the equator or something like that. And so that's the model over here. And of course, you can read off the form of the right hand, this f of xi minus 2, xi minus 1 out of this here. But I forgot to write it down. Okay, so it has this notion then of, because we are dealing with this I mod d, so if I have, let's say, 40 variable model, so x1 is here, x2, x3, dot, there is x40, x39, and so on and so forth. So I have a notion of a distance between these variables. So think of these as, let's say, along the equator. So x1 is very far from, say, x20, but very close to x2 and x40, and so on and so forth. Right? So in this case, the distance along the equator will be effectively something like I minus j mod d. Yeah? And so that's basically the notion of distance in this case now. And that's what we'll see. How does this model evolve in time? These are what are called spatio-temporally chaotic models. That is, what do we see here? What we see here is time evolution of a 40-dimensional dynamical system, so d equal to 40 in this case. That's the index along the x-axis. So at fixed, let's say x equal to 35. At 35, we are basically looking at the time evolution of x35. At 20, it's a time evolution of x20. So this axis is time. And then it's just a color plot. So some appropriate color shading to indicate the time evolution. And so this is what a spatio-temporally chaotic system looks like. That if I were to plot this as a time series, this is what it will look like. Each component does this highly oscillatory complex notion. It has the same properties as the Lorentz 63. You take two initial conditions which are nearby, they will diverge exponentially in time, and so on and so forth. All of those properties exist, actually are valid for this system as well. And I don't think I have done that. I don't know if I don't remember if I have. Yeah, no. This is not in the notebook, but straightforward to do. So what does this notebook do? You first, so that was just illustration of what the system actually behaves like. Each of the 40 variables has a oscillatory behavior. We are going to observe some of those variables and try to estimate all the other variables just from observations of some of them. That's the game. And okay, so that's first part. Sorry, it's not terribly well commented. There are cells with no comments whatsoever at all. Anyway, so I will try to change that before later so that these URLs will remain the same, but I will add comments. So we choose a few random components to observe. That's what this cell is showing, which component is being observed, and some randomly chosen components are observed in this case. And so there is observation operator, which is just projection onto those components. And I guess I can plot the observations and see what it looks like. So this is what observations. So if magenta is the actual trajectory, the blue dots are the actual observations that you get out of after adding the error into the trajectory. Right? So this is the data. This is what we have. This is the information that we are given, and we want to get the estimates of the full trajectory out of these estimates using the ensemble Kahneman filter. Yeah. Okay. It's a fairly, wait, where is my filter implementation? I thought, oh, maybe it's, sorry. Where did that cell go? Ah, sorry, it's here. So the filter is a fairly, this is right now this is not a computationally efficient implementation. It's just a, let's say, word-to-word translation of the mathematical equations. I'm actually not using square root filters, and it's just computing the covariance blindly using Kalman-Gian, which is P H transpose times something inverse, and so on, and just without any concern for computational efficiency whatsoever. But it's a 40-dimensional model, so it's okay. I don't need to worry too much about it. And this is what will be used in this iterative method: forecast analysis, and so on and so forth. Yeah. Okay. So there we go. Where is it? The observations are generated, and then you do filters. What do you need to run a filter? You need an ensemble. You generate an ensemble at time t equal to 0 out of the probability density at time t equal to 0. So some sampling algorithm for initial ensemble, and in this case, the initial ensemble is chosen to be simply Gaussian, so it's easy to sample at time t equal to 0. And this is the initial ensemble out of a multivariate normal distribution. And then the ensemble Kahneman filter, which is forecast and analysis and forecast and analysis in a recursive loop. Yeah. Okay. So what do we want to see? What do we want to see out of this? What we want to see is what happens to this. So here is one of the results, for example. Okay, what are we looking at? The trajectory that I was observing, it's shown here in this color over here. I started with the initial ensemble whose mean and covariance, or in this case variance, square root of standard deviation, it's shown by the shaded bars. So the mean and the standard deviation are shown by the shaded bars and this red line over here. So I start with an initial guess, which is quite far away from the actual true trajectory. Not even anywhere near the actual trajectory. In fact, order 1 difference between the true trajectory and the ensemble mean and the ensemble that I have, right? And so each of these, I guess at each of these observation times, there is a update step happening, which is not clearly visible, of course, because it's too small. And then whenever you go forward in time, more and more information is being obtained from the observation by using the Kalman formula, in this case, because it's a Kalman, ensemble Kalman filter. So you can see one thing, which is that the covariances keep decreasing. Uncertainty decreases. And on top of it, the error, if you wish, that is the distance between the ensemble mean and the variance and the true trajectory also decreases. So you start getting estimates which are closer and closer to the truth with reduced uncertainty as time progresses. And that's basically what happens. Okay, so there are theorems to show that, of course, it doesn't go to zero. The uncertainty doesn't go to zero. The asymptotic uncertainty is controlled by the observational noise. You can't expect the asymptotic uncertainty to reduce to zero. It basically, it's proportional to the uncertainty in the observational noise, which is what you should expect. But actually proving that theorem is not straightforward, highly non-trivial. Okay, so that's one thing, and that actually, so okay, I don't know why I'm plotting it again, I forgot. And this also happens to be the case for unobserved components. So this is again the observed component, but do I have a plot for unobserved components? I don't remember. Yes? No? Not quite. I thought I had plotted, yes, this is the error. Okay, so what I want to now show is what happens to the error. That is the distance between our estimate, which is the mean, and the truth. And this actually nicely decreases almost exponentially with time. It's not quite exponential, but it's pretty fast. And of course, it saturates, the error saturates at a level which is controlled by the observational noise. And this is what is called a ensemble Kalman filter that works, I would say. Somewhere below, there is a case of the filter not working. What does it mean for the filter to not work? So let me just directly jump to that. Sorry, there's a whole bunch of other things in this, but I don't have time to go through that part of the this. So when I do not use localization, that is, localization is not used, here is what the filter trajectory looks like. Okay, so what we are looking here, this is again the true trajectory that is shown in green color, greenish color. The filter starts somewhere far from the truth, and it never really captures the truth at all. But unfortunately, because of the way the filter is designed, the uncertainty in the filter keeps decreasing. So the covariance, or in this case, the standard deviation of the filter will decrease because of the design of the filter, but it does not come close to the truth. So this is overconfident but completely wrong. And at all costs, avoid doing that ever in your life. But anyway, sorry, that's a separate. But really, that's probably the worst possible scenario where the filter is extremely confident. That is, the uncertainty in the filter is very small, but it's completely wrong. And this is called filter divergence. And that happens when localization is not used for these kind of models. Why is localization useful? Absolute no mathematical understanding of why that is useful. So no theorem that says that localization helps in filter convergence. Anyway. Ensemble Kalman filter has been known for about 20 years. The original algorithm is known for 20 years. Localization was implemented maybe about 10 years later because they couldn't get it to work properly. Somebody figured, oh, the covariances are bad. So then they figured out, okay, let's just set them to 0. It worked. And then they just kept using it. So for maybe I would say 10, 20. Actually, sorry, I got it wrong. The real original ensemble Kalman filter was invented in about 30 years ago, maybe 95 or so, 93, 95. And localization maybe about 15, 20 years, something like that. Yeah. Okay, I think that's a good time to stop. And there were a few other things, but okay, I'll stop here for now. And I will just go to the last page. Keep it. Wait, what? It was the last page. Was there a last page? Yes. Okay, I will not read it, but stop here. Thank you.